At the beginning of chapter 6, our goal is really to learn how to take the functions that we learned about in the previous chapters, so sine, cosine, tangent, cotangent, cosecant, and secant, and be able to graph those, and be able to graph variations of those, meaning transformations of those functions. So because of that, what I want to start with is just a quick review of transformations of functions. So if I have a function f of x, so this is my original function over here on the left, I want to understand what it means to make the modification of adding some constant to that function. Okay, so if I see f of x plus 3, for example, it helps to remember that f of x is really just your y value, right? So what we're saying here is that you can take this original function f and add 3 to all the y values, and that's going to be the picture of f of x plus 3. And similarly, if I'm subtracting 1 from all the y values, then I just take the y value I had before, right? Here at x equals 0, it was y equals 0, and then I just shift that down 1. Okay, and in fact, all points are shifted down 1. So we call this a vertical shift. So to put it real simply, when you have a vertical shift, if you're adding a number to f of x, then it goes up. If you're subtracting a number, it goes down by that many units. All right. Now, if we have f of x plus c, where the c is being added within the argument of the function, then we call that a horizontal shift. Okay, let me use an actual example here. So suppose I'm talking about the function y is equal to the square root of x plus 3, where the plus 3 is under the square root. The argument of the function is the part that is underneath the square root. So this I would call a horizontal shift, as opposed to if I had y equals the square root of x plus 3, where the 3 was not underneath the square root, then that would be a vertical shift, as in the last slide. All right. So here's my same original function f of x. If I take 3 away from x, what that actually does is it shifts f to the right 3. Shifts right 3. And if I say x plus 2 in the argument of the function, that actually shifts it to the left by 2. And so this might seem a little counterintuitive, but the way to understand this is that the x is telling me when certain y values are happening. So over here, y is equal to 1 when x is 2. Okay? So if I all of a sudden subtract 3 from the x value, then we can think of this as things are happening 3 units later. So if before y was 1 when x is equal to 2, over here y would equal 1 when x was equal to 5, 3 units later than it would have been. And so then to add to the x tells you that things happen earlier. So the reason this shifts left 2 is we would say that the y values that I observed in the original function are going to happen 2 units earlier than they would have before. Okay. But one other just simple memory device is when it's a horizontal shift, it's kind of the opposite of what you might expect, right? Minus actually means to the right and plus actually means to the left. And that's as opposed to in the vertical shift situation. If I just flip back there real quick, when it was plus, I moved up. When it was minus, I moved down, just like I might expect that it would. Okay. So what if I take my function and I multiply f of x by some factor? Okay. We refer to this as either a vertical stretch or a vertical shrink. So again, remembering that f of x's are just really y values, another way of thinking of 2 times f of x would be to say 2 times the y values. So we're literally just going to double all the y values over here, and that's going to give us our new function. And similarly, when I put a 1/2 in front, that's just the same as saying 1/2 times y. So I'm going to cut all the y values in half. So all the y values that I saw in my original function are now half of what they were before. Okay, but then if I consider a horizontal stretch or a horizontal shrink, then that's when we have some factor we're multiplying by in the argument of the function. Okay, and again, let me just put a practical example up here. If I have y is equal to, let's see here, I guess I can use the square root again. If I have y is equal to the square root of 3x, this is a horizontal, and actually this is a shrink. I'll explain why in a moment. Versus a y equals 3 times the square root of x. This is a vertical stretch. Okay, so here the 3 is outside my square root, whereas here the 3 is being multiplied to the x underneath of the square root. All right, and as you can see here, what's going on is things shrink horizontally when I multiply by 2, and they stretch horizontally when I multiply by 1/2. So perhaps that's the opposite of what you might expect. Okay, but again, we can kind of use the same the same logic that we did with horizontal shifts, in that the x value, or inside the argument, is telling you at what point or when certain y values occur. So again, we'll use the example that when x is equal to 2 over here, y is equal to 1. But to multiply the x by 2 says things are going to happen twice as fast. Okay, so instead of having to wait till x equals 2 in order for y to equal 1, y will equal 1 when x equals 1, right? So twice as fast. Whereas over here, if it's 1/2 times x, we're saying things happen half as fast as they would have before. So instead of y equaling 1 at 2, we have to wait until x is equal to 4 in order for y to equal 1. Okay, so again, it's kind of the, perhaps it's the opposite of the way you would think things work, but again, we see that at play where when it's a horizontal transformation, when it's happening to the x, it may be kind of the opposite of what you're thinking. Okay, and then just a couple other types of transformations to talk about. First of all, vertical reflections. And so if it's a vertical reflection, you're literally flipping all the y values. Okay, so you go from y is equal to 1 and send that down to y is equal to -1. Sorry, I don't know why I wrote x equals 1 there. These should be x equals 2. And then this one, x is equal to -2 and y is equal to -4. Okay, well, we're going to send those up to y is equal to 4. Right, so we just switch the sign of all the y values. Okay, and you can see we get this picture right here. And of course, if we can have a vertical reflection, then we can have a horizontal reflection. So if that negative happens to be in there with the x, then you're just flipping all the x values. So in other words, leave the y values alone and flip the x's. So we send this point 2, 1 over to negative 2, 1, and we send this point negative 2, negative 4 to 2, negative 4, and we of course get the picture that you see over there on the right. All right, now lastly, what we typically see is lots of transformations applied to a graph all at once. So the basic rule of thumb is when you're applying multiple transformations, so maybe you're applying shifts, stretches, shrinks, all those things, then you just need to make sure that stretches, shrinks, and reflections are applied before shifts are. That's really all you got to do. The reason for that is stretches and shrinks and reflections are all about multiplying or dividing things. And shifts are all about adding or subtracting things. So just following the order of operations, we know we're supposed to do multiplication and division before we do any kind of addition or subtraction. So let's do a couple of examples where we apply multiple transformations. So we'll start with f of x equals 2 times the square root of x plus 4 minus 3. And I think what's helpful here is just to go ahead and start with the original function graphed. So I know that if I have y equals the square root of x, then we start at x equals 0. That's the first value in its domain. And of course y equals 0 there. When x equals 1, y is equal to 1. And then when we're thinking of square roots, we think of the next perfect square. So when x is equal to 4, y is equal to 2. And I guess the next convenient one is x equals 9. That takes me a little off the page, or off the grid there, but that would give me y is equal to 3. So that'll give me a pretty decent picture of my original untransformed function, y equals the square root of x. Okay, a little bit wobbly there, but we get the picture. All right, so now let's talk about what those transformations do to this function. And I'm going to go ahead and use red to indicate my function f of x here. So I see the 2. The 2 is a vertical stretch. And I know that it's a vertical stretch because it is outside the square root. So it's outside the argument of the original function. So the square root would be the, what's inside the square root would be the argument. And so the 2's outside, so that's definitely vertical. And speaking of vertical, this minus 3 is also a vertical transformation, but this is a vertical shift. And remember, vertical shifts kind of go in the direction you might expect. So this is down 3. All right, then lastly, this plus 4, this is happening inside the argument of our function. And so this is a shift. And I'll go ahead and indicate that it's a horizontal shift. Horizontal shift. And then remember that this kind of goes in the opposite direction you might expect. Or think of it as things happen 4 units sooner than they would have, so it's going to go left 4. Okay. So what I know here is that this vertical stretch is going to double all of my y values. Okay. But this vertical shift down 3 and the vertical shift left 4 is going to change the location of all those of this starting value, and then from there I'll follow the behavior of 2 times the square root of x. So let me kind of use an intermediate color here just to kind of do this in a couple of stages. So first I might be interested in saying, okay, well, let's do y equals 2 times the square root of x. What would that look like? Well, 2 times the square root of x doubles my y value, so this y value goes here, this one goes here, and then this one goes up to here. All right. So you can kind of picture someone grabbing my black square root of x function that I had originally and just kind of stretching it. It's kind of pinned down to the origin here, but everything else gets stretched up. Okay, that's kind of a nice intermediate step. So that's what I mean by applying stretches or shrinks prior to your shifts. And then with that knowledge secured, we can then talk about, okay, well, what does all this shifting do? Well, it shifts things down 3 and left 4. So this is my new starting point. So this is, this is where my this is where the origin went to. Okay, and then I make it behave like this blue function from here. So I would go over 1 up 2. Okay, my blue one over here went over 4 up 4, so I'm going to also go over 4 and up 4. And this one went over 9 and up 6, so I'm also going to go over 9. So 5, 6, 7, 8, 9, and up 1, 2, 3, 4, 5, 6. And so this is going to be my function after being transformed. All right, so let's take a look at this other one. This one is clearly shifting a parabola around. So we know that plain old y equals x squared, right? We know that that is going to be at the origin to begin with. Then we're going to go over 1 up 1, over 2 up 4, over 1 up 1, over 2 up 4, and I guess I'll go over 3 up 9, and left 3 up 9. Okay, so there's my original y equals x squared function. Okay. All right, so what have we done to it? We have, it looks like, multiplied by 1/2. So, and that is clearly outside of the argument of the function, so this is a vertical transformation, and it is a vertical shrink. A vertical shrink by a factor of 1/2. And this is a shift up 2. And then remember, now this one's in the argument, so when it says -2, that actually means right 2. We can think of this as y values are happening 2 units later than they would have. Okay, so from here, we've got, and I'm going to try to do this one without doing an intermediate step, just to show you how that works as well. So certainly doing a little intermediate step like I did in the previous problem and graphing y equals 2 squared of x, that's a good idea. But what I'm just going to do is first understand that this shifting changes my vertex, right? Changes my vertex from 0, 0 to, I'm going right 2, up 2. So this is my new vertex. So the way to just immediately do that and then to make sure that you get the appropriate vertical shrink is you would say, typically from the vertex I would go over 1, up 1. But because I'm multiplying by 1/2, I'm only going to go over 1, up 1/2. So I'll just go up half as high as I would have if it were a normal parabola. Normally I'd go up over 2, up 4. But because of the fact that I am cutting it in half, cutting all y values in half, I'm going to only go over 2, up 2. Okay, and then normally I'd go over 3, up 9, but half of 9 is 4 1/2, so I'll go 1, 2, 3, 4 1/2 up. And so that gets me my transformed quadratic function. All right, so just to solidify things here, I kind of want to do one big example that is a little more abstract because it's not using a particular function that we're comfortable with necessarily. And then it has us apply all four of the main types of transformation to it. So here's my original function over on the left, f of x. And then over here on the right, it's telling me what to graph. 2 times f of 1/2 times the quantity x minus 2, and then minus 1 to all of that. So what does all this mean? Okay, so let's go through and let's identify this stuff here. This is a vertical stretch because it's happening outside the argument. This is a horizontal because it's happening in the argument of the function. And remember, it's 1/2, so actually this is also a stretch because things are happening half as fast. My minus 2 here is a horizontal shift, so I would say shift right 2. Okay, and it's right because things are happening 2 units later when I say minus 2. And then lastly, this is a vertical shift down 1. So what I want to do is look at this original function and know that all of this has to happen to all of these points. Okay, and I would say when in doubt, it's probably a pretty good idea to go ahead and do an intermediate step. So I think what I'll do first here is let's apply just the vertical stretch and horizontal stretch. Okay, so first in blue here, let's just do this. 2 times f of 1/2 x. So this 2 tells me to double my y values, and this 1/2 tells me to double my x values as well because things are happening half as fast. So this point here was the point, -4, 2. So I'm going to double both those numbers. So double that to 4, double that to -8. So now I'm at -8, 4. This point here was -2, 4. And so we will double the 4 to 8 and double the -2 to -4. And then here, looks like we were working with 1, -3. So now we'll work with doubling the -3 to -6 and doubling the 1 to 2. And then lastly here, this was the point 3, 2. So then that becomes the point 6, 4. So here's my intermediate step. And of course I'm going to connect these up best I can. And this one will be interesting for me on the computer here. I didn't do too bad of a job except at the beginning. And then there. Okay, so there's kind of my my intermediate step. Okay. All right, so now of course I've got to apply these shifts, but that once I get the doubling done, that's the shifts are much easier. So I know I'm going to the right 2 and down 1, and just so that I keep this a bit cleaner, let's see, let's use a, what color should I use? I guess I'll use green. So this whole thing I'm going to go ahead and graph in green, but I'm going to do that over here where it's a little cleaner. So we had that point -8, 4, so starting here, and then we're shifting to the right 2 and down 1. So right 2, down 1. And then my negative 4, 8, I'm going to shift that to the right 2 and down 1. 2, negative 6 puts me there, so I'm going to shift that right 2, down 1. And then lastly, 6, 4. 6, 4 is here, so I need to shift that right 2 and down 1. And so my transformed function should look something like this. Okay, and you'll forgive me for my sloppiness here. It's kind of hard to do these straight lines on a computer sometimes. So hopefully this kind of jogged your memory about transformations of functions. And if you take the time to kind of go through this and get those cobwebs dusted out of your mind about transformations, I think you'll find the graphing of sines and cosines that we're about to embark on much easier.